Okay, good. So actually, what I'm just gonna, if we're gonna talk about is giving you a little brief background again. I mean, you're probably all familiar with the, the storms, Irene and Sandy. Then we had a bunch of, with the data we used, we had a bunch of data from before the storm and after the storm, and the main approach to identifying where the sediment went is kind of comparing these two data sets. And then, we use this data to determine where we might see change in the river, and then basically trying to quantify using different methods the changes in the position. And then the second part is actually because, as Dennis mentioned, there was a lot of input from different tributaries. We were going to see can we quantify like how much is coming from different tributaries, or basically like can we identify different sediment types coming from different tributaries, which might also help us in the future, like understanding the sediments a little better. Okay, this does not. Now that we go. So that's the background about the two storms. So if you maybe remember, Irene hit the area in 2011, and we got the second Hurricane Sandy in 2012. And the two storms, they were both are big storms, but it took a slightly different path, as you can see. So in red here, the Irene basically went over, the center went right over the Brooklyn, and then went further north, and then it lingered a lot over the upstate New York, and it caused this heavy rainfall, similar to what we've seen in the other storms in the last couple of years, where these hurricanes, they maybe don't bring a big tidal wave, but there's a lot of rainfall, and this caused a lot of flooding upstate New York and all the tributaries of the Hudson River, and with this flooding came a lot of sediments. Sandy took a slightly different path here in green, and so it actually made landfall in New Jersey, and for some reason there wasn't that much rain in upstate New York, also maybe because it took a different path, but because landfall was south of New York City, we got all the wind is pushing up all the surge, and we got this big surge of tidal or storm surge hitting the Hudson River on the harbor, which caused a lot of flooding and maybe moved some of the sediments, but there was maybe less sediment input through Sandy. So we have like two different storms with different effect here, and I think there's also the other thing. In 2011 there was another storm, Lee, which wasn't a hurricane or not even a tropical storm anymore when it hit New York. That's why, if you go to NOAA on the website, they only give you the track data when it's tracked as a hurricane or tropical storm, but it still caused a lot of rainfall in New York State. So it was, 2 weeks after Irene, we had another event that caused a lot of rainfall. And what we see here, we're actually lucky doing Irene. That's basically data from the Irene time. USGS had a lot of monitoring stations out along the Hudson River. They always had 3-4 permanent stations, but they had some additional that year, especially in the tributaries. Let's see all the orange dots on the map. And the left are the different USGS stations, so they can monitor the input very well. And if you look at this chart, it's just the water running down. You can clearly see the two events. First, we see Irene hitting here, and then 2 weeks later, we got a big second pulse. That was the rainfall linked to the storm Lee. And from all the monitoring station, USGS, they kind of estimated there was a total of maybe like 2.7 million tons of sediment dumped into the Hudson River. Just to put in the perspective, so usually the annual load of sediment throughout the whole year is between like 700 to maybe like 800, 900. A big year maybe gets to 1 million tons. So basically this double event, there's two events in a span of 2 weeks, delivered kind of the 3 times or more than 3 times the annual load of sediment into the Hudson River. And through a monitoring station that USGS is running near Poughkeepsie, they had monitoring like how much sediment was passing by, and they basically saw that, 1.5 million tons of suspended sediment was washing through, like south of Poughkeepsie. You've seen all the brown in the previous satellite image, but over 1 million tons of sediment was basically somewhere north of Poughkeepsie in there. The question was, where is it? Because it wasn't really supposed to be like a big depositional area north of Poughkeepsie, and so we went basically with help from the Hudson River Foundation on the quest to find if we can identify where the sediment might be. So the other thing that also was mentioned is that something special, that's maybe why there was so much sediment in the Hudson River, was a lot of the sediment came actually from the different tributaries, especially the Catskill Rounder tributaries, which is also unusual. That usually most of the sediment that goes in the Hudson River comes from the Mohawk River, a little bit from the upper Hudson River, which is the big watersheds up here, the Mohawk River and the upper Hudson. But now we got a lot of contribution from the other tributaries there. And the question was if we can, with so much input from the tributaries, could we trace sediments from different tributaries as well? So our main question was, okay, what happens to the sediment that got washed in by the storms? And our hypothesis was kind of, okay, so we've analyzed some of the Hudson sediment distribution before, and we found some depositional areas. Our hypothesis was, okay, maybe looking, it gets deposited where it usually gets deposited, just more of it this time. So we're going to look mostly for those. And then the second hypothesis was that, okay, with all the input from the tributaries, we might be able to identify and trace the sediments from the different tributaries. To analyze how much we got, we used a lot of pre-storm data. So between 1998 and 2004, the New York State Department of Environmental Conservation, they funded this big mapping project in the Hudson River, which kind of created a baseline of data. So we collected detailed bathymetry, we collected sub-bottom data, and we took a lot of sediment cores and graphs, basically for the entire Hudson River from the harbor all the way to the dam in Troy. And as a result, we had a very good idea what kind of sediments were distributed, like these to the surface throughout the system with like mud, with sand, and we also identified different sediment environment, and especially areas of deposition that you shown in red, where we thought that, looking at the sediment where we think it was basically depositional. And we used those data as the best baseline, and then collected a few new data to compare the difference between those. I mean, there was a multi-year project, and it was not really feasible to really repeat the whole survey of the Hudson River. So we kind of selected a few study sites to kind of where we either thought that, well, first we had to have good pre-storm data for some of the areas where we thought that we had like the positional site where we would expect the sediment maybe to go, and then we also wanted to look near the main potential sources from the tributaries. So that's why we choose those areas. So we knew Haberstroh was a traditionalistic big depositional site, and we had very good data, so we wanted to look there and make a comparison. And then we focused mostly on the north, like between Poughkeepsie and Kingston, and north of Kingston, near the Esopus and Catskill tributaries, and looked there. And then we had a small area near Peekskill and the southern part of Newburgh Bay that we were looking at data. And we went out and collected sub-bottom seismic data. We were following the old lines that we had previous lines. We kind of reshoot the lines with the idea to compare those and then analyze the differences. And then we were also taking sediment cores wherever possible. We tried to take a core near where we had an old core so we can compare those. Although we didn't have that many cores in the upper river, so mostly because a lot of sand there, which is not easy to core. So there's like not so many old cores. And then we took all the data and compared the new with the old data. How we do this, this is seismic or sub-bottom data. So this is and like from Observatory, an example is in 2001, and then the new data set, and then we can basically compare the surface. And sometimes it's a little difficult to get the vertical right, but the subbottom has the advantage that we also can trace some of the older horizons, which of course not, they're not going to change. So we have a reference point if you want to compare the subbottom data. And you can see that maybe here this is not so much, but here already visually there is quite a change in the center where there was a dredged and then later refilled in the center of Observatory. So we take this, we trace the bottom of the river and the older the new data, and then we compare those basically, so we can plot them on top of each other, make sure that the vertical as well, and then we can calculate the difference between two, and then areas that have where we see a positive change, like where something has the positive stick out, and areas where maybe some sediment was washed away stick out, and we take all those data and all the lines we took, and we can color them by depth. So red is basically here, and also in the future plots shows kind of a deposition and a shoaling of the area, and in bluish we have indicate lost sediment erosion, and we think we have probably like a, if it's like plus minus like 10 centimeter, that's really like the resolution. Then it's a little uncertain. So everything in yellow, it's kind of, we can't really say if it's like deposition or erosion. This is kind of the limit. But with red or blue, we're pretty certain that we have erosion, and we take then all the individual line data, and then we kind of interpolate to come over a grid that we can use for volume calculations. And good. And then the second part is we had sediment cores, so in different areas, and you can sometimes in some of the sediment cores you actually can visually already see differences. Light brown to dark brown, that indicates that there was like different layers of sediment. But our main method was we were kind of more like TIM domains. We're kind of measuring metal content along the core length. So every like 10 or 5 centimeters, we took a measurement of what kind of the metal content is, and then we can compare those. Usually it's a characteristic curve for a certain core. We can compare those between old and new cores. And we have using an X-ray fluorescence system that's a very rapid measurement of a series of different metals in the cores. So what we're getting here, as an example, we're not only getting like lab, but we get the whole range with this method simultaneously of metal types. So we can get this individual profiles, and then kind of, shifting we get a profile for the old core, we get a profile for the new core, and often, with the beginning of industrialization or certain input in certain areas, you get a certain peak or spike in the metal content. So we're kind of shifting the curves up and down to see like where those across the board of most of the elements kind of match to both, and it gives us a fit. This is a core here, for example, where so in black is the old core and red is the new core. So if we shift all the peaks up, we actually have to shift the new core down. So it seems to be that here is almost like 30 centimeters, like 29 is kind of missing from this spot that was there in the old core. So here would be an example from erosion. And we can do this for all the cores we took. Another thing that we originally didn't plan to do was comparing bathymetry, which would be the best, the more direct way in an area to compare the whole thing, but collecting this data is pretty expensive. So we didn't really do it, but we were lucky. So towards the end of this project that NOAA actually went and took some repeat bathymetry measurements in some areas, and also the New York State DEC has collected some newer data in shallow water areas. And it was actually interesting. NOAA was actually doing this survey because there were reports that from the pilots in the Hudson River that there was actually some significant changes in some parts of sediment bars and things upriver that might, there was like one barge running aground at one point, so they really wanted NOAA to reinvestigate after like Irene and Sandy. So anyway, we got hold of this data here, and we can use actually new bathymetry on the old one that we collected in part of the Hudson River benthic mapping program earlier to compare directly the depth change. The only problem is that the overlap between these two data sets is not always very good. So in the original data, we kind of excluded all the shallow areas, and the new DEC, basically shallow water survey, concentrated only on the shallow area, so there's very little overlap between these two. And NOAA basically only went into the main shipping channel to collect new data. So for this stretch north of Kingston, for example, on the left is the bathymetry data that we collected originally, then the combined new data is in the middle, and then what you see in the third panel here is just where all the new data overlap, we actually can compare the data set. So it gives you some extra information, but it's unfortunately a bit limited in the spatial extent. And more complicating is also here that because all the different data sets were collected with a slightly different vertical reference, so we kind of had to manually shift things a little to kind of make a good fit, which always creates some uncertainty and error in there as well. There's no Aperware doesn't have a fixed permanent vertical reference point, so every survey basically creates their own vertical reference. Another thing we also did, so parallel to our observational study, Hudson River Foundation also funded a model study of the work done by Dave Ralston and Rocky Gaia at Woods Hole. So they kind of created a hydrodynamic sediment transport model for the Hudson River and put in the rain and suspended sediment load from Irene, and they modeled like where it would go in just using the physics. Dave also kind of gave us the model output, so we have the data what they think where the sediment went 1 month after Lee happened. So we can use and compare those as well with our data that we have here. Okay, so this was all the different data sets that we basically used, and the idea is that, okay, if you use multiple data sets and compare those, then, if they all agree, then we're really confident that, okay, this is where sediment goes, and if there's discrepancy, then we have maybe less confident. And I'm just going to go through the different areas from south to north now. So we're starting in Hubbardsville Bay. This is an area where we've done a lot of work previously, so we had really good baseline data. And you can see here on the left, basically all the line differences and the core locations. Then we have interpolated this area, and you can see that it's actually, we see areas of some erosion on the shallower parts. We only concentrated on the main channel here because that will be understood would be the main deposition area. But we see a lot of deposition in the center here, which is where they usually dredge the navigational channel. They dredge it, and then it's basically collecting sediments afterwards. But we also see a lot of sediments up here in the north east as well. For here, we have also another bathymetry survey from 2013 done by Stony Brook University that we can compare to the survey they've done part of the Hudson River benthic mapping study. And again, we see like a lot of change, very similar to what we see in our sub-bottom analysis, the main change in the main channel and some deposition up there. And just in case if you're wondering what's happening here, so there's a lot of deposition there. So that's the entrance to Hubbardsville Marina, which basically, I think they dredge out occasionally, and then it gets refilled by sediment. The model shows quite a graphs and shows a lot of sedimentation in the center part too. General picture, but not necessarily exactly the same one. But I think that the model resolution is probably not good enough to really resolve the dredge channel and like the marina channel. So there might be some issue, but kind of I show quite a bit of sedimentation in Havasphere as well and erosion. We can compare this with the cores. So that shows series of cores. So you can see that here is like we have a deposition. So positive numbers is deposition like of 10 centimeters. So the new cores is the top is like higher, so we shift the old core down for comparison by 10 centimeter, which kind of fits our area here, which is like plus minus, the yellow is plus minus 10 centimeters. The same here, we see a lot of deposition for some of those cores that we took in the center. Here it's like almost like 45 centimeters. We have some erosion up here at the edge. So there's a mix of them. They're broadly following the same pattern. There's some, they're not exactly about the same centimeter range, but it's usually in the range of the uncertainty that we have here. Basically, see the big deposition in the main channel and very little in the outer channel, and even some parts of the shallow parts on the western side, for example, some erosion or non-deposition there as well. So if we sum up for Havasphere Bay, we see already here that the deposition is not uniform. That's a lot of deposition is in the main channel, in the northeast corner of the channel, and we also see erosion of these corners. Again, here we have to say that so this is data that we collected, so the change incorporates both like Irene and what happens after Sandy, and it's quite possible that, for example, maybe Irene deposited some more sediments everywhere, but then the big, surge and flood with Sandy might have moved things around and maybe like cleared out some of those shallower areas on the sides. So what we do see is a combined effect. We also actually have to say, because the data that we collected originally with the benthic mapping, they were like collected in the early 2000s, and then Irene, the data we collected after the storms, we collected in 2013, 14, so it's like more than 10, it's like 10 years, a little more than 10 years difference. So in addition to the storm effect, we probably see the long-term changes in the Hudson River as well. We didn't originally analyze for the old data the long-term effect of what we think might happen in Havasphere Bay. So we would expect over 10 years, maybe something average from like a centimeter to 10 centimeters deposition, but we find like 10 to centimeters to 30 centimeters, basically a foot. So it's definitely much more sediment deposited there than we originally would expect from the long-term trend that we observed before that. All right, moving on a little further to the north. So we did a few survey lines near Peekskill to see what's happening in the Hudson Highlands. And what we do see, so we don't have a repeat bathymetry data, so it's pretty deep there naturally, so NOAA doesn't go there for surveying. Resurveying, but we do see that there is a bit of deposition on the side where it's a little, maybe even erosion in the middle of it. And if you look at the core that we took on the side, it actually shows also like 50 centimeter change. The data have to take a little bit cautious because the slopes are very steep, so it can make quite a difference if you just like, if you're not exactly at the same position comparing all the new data because it's very steep. But definitely it seems to be also fitting the model that near the sides we see some deposition where in the center maybe some erosion even. When yeah, I mentioned that already. So only small area. So we did a little bit in Newburgh Bay. We didn't expect to be there too much deposition, and so only surveyed a little corner in the south of Newburgh Bay, but we did see some deposition on the sides, a little maybe erosion in the center of the canal, which fits the general pattern of the model. But the model exactly, in general, even if you go further, shows that actually much more deposition in Newburgh Bay than we expected. So unfortunately, we didn't do the whole Newburgh Bay area, and we had what we compared like one core here, like in the south, which actually shows also like 17 centimeters of deposition. So there definitely is some deposition there in the side, but maybe even in the center there might be some erosion going on. Then we went further north. We did quite a bit of surveying between like Poughkeepsie and Kingston. Kingston is here. Roundout Creek is just the north of this section. And so here's again, and you see that there's not a uniform pattern of deposition erosion, that in some areas, especially again near the shoals on the sides, maybe around this bend here and over there, there's quite a bit of deposition happening, but others points they show erosion. In our data, there's very little bathymetry overlap because we only had this DEC survey of the shallows there that shows a bit of deposition in the shallows there, and there's also an area where the model shows deposition that shows some erosion in the center. We have a little more deposition around here that I don't show, and the cores also show different pictures. There are some areas where we don't see much change in the sediment cores. There's others where we see maybe like half a foot of deposition, and another one down here where it actually shows to indicate some erosion is going on. But you know, altogether it's quite a large area where we think there's deposition happening. Again, there's some uncertainty here, the slopes of the sides too. Then we went further north. That's the area north of Kingston, so the Roundout Creek is now at the bottom. The problem here with the data that we have is that this is an area now we come in the territory where there's a lot of sandbars in the middle, so it's hard to go with a boat back and forth. So we only have a line on each side, and then a few more data down there near the Roundout Creek. So we see a pattern of erosion and deposition in some areas where the bathymetry survey seems to be mostly showing deposition, and the model shows a little bit of deposition on the side, but not much happening. And I think there's also an area where kind of the method gets a little more tricky, because we actually, a lot of the deposition that we might see in erosion might also depend. What we might see is just a sandbar, the big in the center here, that's where we have no data is a big sandbar that might just be shifting. So, you know, if it shifts, one side is eroding, the other one shows as deposition. There's a lot of big sediment waves in the center that also moved a lot. Anyway, our data seem to kind of link pretty well with the sediment core. So the one in this area shows only like very little deposition, the same as there, and then here near the shoreline there might be, but we don't have a good overlap between the metals. There might be pretty thick deposition, but there's a lot of uncertainty going on. Definitely we can say that there seems to be, again, a variation of deposition erosion, so it's not all like depositional. And we do see the effect of migrating sandbars and sediment waves. And the same is true if we go further up to the Sopos Creek issue measure. So we do see a little bit more depositions like north and south of the creek mouth a little, which is maybe similar to what the model shows. But then it's a lot of back and forth, and it's kind of washed out if you kind of interpolate here. But if you actually look at the individual data, you see there's a whole bunch of deposition erosion, which basically again is like probably the sediment waves. And so we have a sediment core. We don't have too many in this area, but it's not very conclusive. There might be some deposition here, which is like 5 or 10 centimeters. And then we have the final stretch to the north. We looked at the Catskill and south, where we do have a lot of bathymetry data. We ourselves have the 1 or 2 lines because again it's really getting narrow there, and there's a sandbar in the middle, which is a little difficult. But there seems to be some again pattern of deposition erosion, but not too much. Interesting enough, the north comparison seems to be showing some erosion, but I'm not sure. That could also be related to some dredging that has been done in the area in between. And the model shows actually a lot of deposition in the shallow areas, but we don't really have our data don't go on the shallow data. We didn't have previous data going there. And I also just can use this here. That's actually an example of if you look at the bathymetry data from this area, you actually see the difference. These are basically sediment waves. You can see how they have moved or changed over time. So a lot of the pattern that we might see here in terms of deposition erosion might just be sediment waves moving a little bit in location. So whereas everything here would be positive, would be a deposition, that would be an erosion event. So indicated. Good. So we interpolated values. So because everybody wants to compare our findings with the actually like million tons of sediment that's stored. So we did try to quantify those, but there's I still think that mostly it's better to just compare the patterns rather than actual numbers. So I guess there's maybe some idea of the bulk part of what it is. And so from our method, we're basically getting volume of change, and we're using some dry bulk values here to calculate this, convert this into tons. We have a lot of, we actually measured the density of this dry sediments throughout the river from a lot of surface samples, and it's a little higher in the upper river because we have more sand particles, and then the lower part has a lower dry bulk density, is more mud sediments. And so what we find, well, we do find that in the Super's Catskill there was maybe a little less than 500,000 ton eroded and deposited, not much net change. So this is a number that's probably in the range of uncertainty for sure. There was a lot of change, even a net erosion maybe between Kingston and Sopos, but again, I would think we don't have very good data. So this a number that mostly contributes to the shift of the sandbars and sediment waves. But interesting enough, so we get over 1 million tons between Kingston and Poughkeepsie, and because we have more data there, better data density, I'm more confident with this number. So I think this might be where most of the million ton of sediments is probably located. It would fit the numbers. I mean, you don't give too much on the actual numbers, but the order of magnitude is right. It might actually has received some sediments from the north of Kingston as well. And we don't see much change, like in average in the Newburgh area, but then we might have missed the northern part of Newburgh, where a lot of the deposition might have happened according to Ralston's model, and a little bit of deposition in the Peekskill area, but then also like over 500,000 ton in the Haverstroh Bay area, which again, because we have better data coverage there, we are more confident that this is realistic. So, and some of the other sediment might have ended up eventually in Haverstroh Bay over time, but there might have been also a lot local stuff. So I think that most likely most of the missing sediment is probably in the stretch between Kingston and Poughkeepsie. That's what we think.
Frank, what's the time frame then?
Oh, the time frame would be between the original data collected like, around 2000, 2004, and the new data is like 2014. So it's a time frame which, as I said, it's the effect of the two storms plus any long-term change in migration that might have happened. So there's also a lot of things kind of shifted in the a couple of years after the storms and our survey. Anyway, to sum up this part, so I think we do think that a lot of the deposition, the new deposition, is actually happening in areas that we expected as depositional before, plus maybe in some areas that we didn't expect that much. But we also saw that some places actually got deeper, so it was not only sediment added to the system, but that makes it more complicated. Some other stuff was shifting around. This could be part sediment, like moving sediment waves and sandbars, but maybe the big flooding events also eroded sediments in some places. And so there were differences in some places between the different methods and the model, but I think the overall pattern, at least, I think is pretty consistent in general where it is. And the major deposition areas that we identified as the stretch between Poughkeepsie and Kingston and Haverstraw Bay. So most of it is ended. But there's other areas we didn't look like a part of Newburgh Bay. And so there's remaining quite a bit of uncertainties. And just like reminding what you already said, that we have what we see is a combination of the deposits from Irene and Lee, the changes caused by Sandy, but also the long-term effect over the stretches. So that's confident.
Yes, it looked like the net result of all the pluses and minuses is negative.
Yeah, I think it's mostly because if you go back, I think the net might be, but it's mostly the number because of what's happening between Kingston and so forth. And I don't trust that number too much, because some of it, if you shift the vertical between the old and new data, you can change the number. But yeah, so that might be slightly negative, or might be might have moved somewhere else where we don't see, where we didn't look. That is impossible too. Good. Okay, so this is kind of wrapped up my part. So the second part is we looking a little more at the chemical signature, and I think Kenna is doing that part.
So as Frank said, the large amount of sediment put into the system from distinct sources, as we saw from some of the monitoring data, gave us an opportunity to study, could we detect this pulse if we think a lot of materials coming out of Catskill? Would it be chemically distinct, where we might be able to actually trace that and resolve the fraction of, say, Catskill sediments in a sediment taking downriver? Kind of a tall order. It's a complex system, but this was a nice opportunity to see if we couldn't see if there's geochemical signatures that could be developed. And so what I did was, and we had a large data set of archive samples, and then we were able to collect new ones, and so we were able to do a bunch of different comparisons. But the main hypothesis here was that that sediments derived from different sources would have different geochemical signatures. And that they could be used to identify and hopefully quantify inputs into the Hudson system. And so if we can identify them and trace them, we might be able to start resolving and predicting inputs from different places far afield. We're not there yet, but we're getting there. Okay. Okay, so Frank has talked some of this, but I we had over 600 chemical analyses we did for this study on archive samples. So we had a large selection of cores and sediment grabs we were able to pick and choose. And so that would establish our background. And then that was the before, and then we went out and we did collect new cores. And also because I was interested in what was coming out of the tributaries, we did our best to sample tributaries and to characterize the material. So the tributary sampling was difficult, not the same as sampling on the river. And we focused initially on the big three. Does this laser work? Oh, look at that, sort of. Not really. No. Oh, not on the screen. But we focused on the Catskill, Catterskill, the Esopus, and the Roundout, given that we thought that was where a lot of the action was occurring. But it turns out, as we develop some of these techniques, what happens before is also important. So, you know, we learn as we go. But so we don't have every single watershed and every single tributary characterized, but as you'll see, we'll still able to discern quite a bit. Okay, so this is sort of divided into two separate endeavors. First, it was just, we're going to characterize the sources, and we do that two different ways. One, we can just compare the chemical composition between the estuarine samples, so those that were collected from the main stem of the river, and then also compare it to the material we were able to sample from the tributaries and see, are they consistent? Do the patterns that we see coming out of the tributaries, does that largely explain what we're seeing in the river? And so that's a fairly straightforward element plots, a good way to start exploring the data to see what we can see. And then the second part of that was, so basically ignoring the tributaries, those samples, we can just focus on the estuary samples, and we can characterize material between each tributary with the idea that that would be mostly influenced by the nearest tributary. And so we could look for changes. You know, we get material just downstream from any given tributary. Do we see a change from before, upstream and downstream, that we might be able to say, well, there's something odd going on here. We can attribute that potentially to a tributary or maybe a process. And then the second part was we used our data and a couple of different statistical tools to try and resolve the fractional component. Can we identify what's coming from where and how much? And I won't get to the last end member mixing analysis, but I don't have time to do that. Okay, so the fine print. So in some sense you have to sort of, we know other things go on, especially in the estuary, but for this study, we've had to simplify. We made some simplifying assumptions, and I think the main one there's definitely some reactions going on, but in this case, it doesn't appear that we see too much. Maybe downstream we do, but so we're going to assume that that sediments coming out of the different rivers maintain their identity, and that we're just looking at a mixing, and that you don't see significant impacts of various processes such as dissolution, precipitation, adsorption, desorption. So no real transformation. That if we see something in the tributary and then we can identify something similar in the main stem, we're going to make that connection. But as you'll see, there's some questions that need to be answered still. That's probably so we know that as the salinity increases, there are some desorption effects. So I'm not fooling myself thinking that there are none. But for this study, and most of it really is focused upriver in the fresher portions, but we do have a lot of samples downstream. The good thing about this, so not only are we coupled, so we have a lot of material coming out of a few tributaries, so maybe that increases our chance of being able to identify it. The linear nature of the Hudson is really what makes it work, I think, because we have a lot of control. We can look at some samples and know that they're not influenced, significantly at all by downstream tributaries. So the further north we go, the simpler the system gets. And so that's also, you know, as we add complexity, what changes do we see and what can we say from that? So, buyer beware. Okay, so the first thing that I did was what we call bivariate mixing plot. So just elements versus elements, both the tributary data and the tidal Hudson samples were compared. I'm not going to go through every single plot. I won't torture you with that, but I'll just show a couple of examples of each of these techniques and how I think they're useful. But you know, in this case, they allow us to compare different sources and look for differences. Are there, as we examine the tributary samples, do we see unique patterns that we can identify? You know, wow, there's something unique coming out of that tributary, or it's all the same. Do we see? We're looking for linear features, geometric features like triangles and other things that might show mixing between discrete end members. It also allows us to compare. If the tributaries, when compared to the main stem of the river, look nothing alike, then one of our assumptions is definitely wrong. So what have I got here? Okay. So this is just an example of potassium versus iron, and what I did was, so I don't expect you to be able to read that. That was more for me as I was going through it. But what we have is the large triangles in both cases are the tributaries that we sample, and so nothing south of the roundout. So those are the tributaries we have, that and north. So and what I've done is I've divided the river into two parts, and you'll see this sort of pattern in some of the other work that I've done. But so this is north of Poughkeepsie. So ideally, the estuary samples and the tributaries are going to be a closer match. And then south of Poughkeepsie, we have no tributary data, and so those are the same. This is the idea that, like, well, maybe Mohawk, Upper Hudson, and all the other main tributaries. How much do they impact further downstream? And what I was doing was, one, is it consistent? Do we see things that don't make sense? And then what changes happen that might allow us to identify a process or perhaps the influence of another tributary? So it might guide us where we might sample next. So there's more work to be done if we wanted to characterize this. We also see shifts in the data. This is, you know, whereas sort of if we were to sort of draw the centroid, it's going to be further down here, and then we see a shift. Most of the data in the sort of the lower portion of the Hudson, it increases. Now it's linear, so you could just be adding more of the same material. A lot of this, you know, there's not really a. This is more of a signature. There's not really a mass balance going on here, which is one of the problems. But it does allow you to identify areas. And so let's see if I can put another one in. Okay, so I think I pretty much just went through that. But so this middle point here is we see a lot of variability within the tributaries, and so there's material coming in. But just because you have a unique signature, and you see that in the estuary, it doesn't mean that one came from the other, because it really is a question of how much material comes out of the river. So you have to be careful. And so, you know, we can sort of presume that, well, look, that really matches, but if we don't have how much is coming out, or it's very small, it's got to be something else. And so, but you can, so we can now sort of leave the tributary data for a little bit and just think about what we have in the estuary and look at how changes occur downstream. So now we're just going to go a transect from Albany all the way down to the harbor with the data that we have, and look for changes in chemistry. I think I get to it in the next slide, actually. Okay, so I wanted to talk a little bit about so how do you start to push this together so you can work with it. And what I decided to do was, where we had you know, we have samples that are between two tributaries. What I did was I calculated the median and the median deviation of every, you know, the elements in that zone, and so that zone then would be identified with a certain values. And then for each zone, we can plot that downstream. And we're looking for changes. What we observe is we see significant changes between adjacent zones, so that might tell us something about a material coming in from a particular tributary. We also see larger trends in the data as you head downstream. So I got a few of these, and again, so each bar is representative. The width of the bar is the distance between tributaries, and in some cases we didn't sample all of them, and the distance doesn't really determine how important that missing tributary is. So, it would be nice to complete that so we can evaluate that. We also, in some cases, we have a whole lot more samples for a particular zone than others. As Frank's mentioned, sometimes getting samples in the upper part can be difficult. And so some of these have only a few, and so there's probably a little bit of uncertainty introduced there, but in general, we see, so for several of the elements, potassium being an example, we see sort of elevations, we see a dip, and we see this in almost all the elements, sort of a lower values here, and some dramatic rapid changes between, estuary zones. We see a gradual rise, and then a decrease as you head out into the harbor. So I've noted the positions of Haverstraw Bay and then the George Washington Bridge, and if we're thinking about, say, turbidity maximums where sediments tend to concentrate, the study wasn't necessarily about that, but that's something to think about as we look at the data, because there are other processes going on as well. So lead and zinc pretty much look similar, and they're contaminant metals, so they have a timing. They've changed through time. Some of the other elements haven't. You can't imagine potassium concentrations have changed dramatically over time. But lead and zinc and some of the other contaminant metals certainly have, and we can see this. We see this trend of fairly this steady increase. We see changes between what's going on here. We see a dramatic increase. So as you get closer and closer to, say, the city and industrialization, that's probably something going on there. Because we have, there is an age impact, so sediments of a certain age will be carrying a higher contaminant load, and either newer or very old sediments will be less. So you have to, so there's some somewhat confounding factors when you think about trying to use the contaminants themselves as a tracer, but we see that. So zinc and lead, strontium and calcium, these would be ones that go, again, we see this sort of dip, but it tends to just increase as you go towards the ocean. And strontium is fairly high in seawater, as is calcium. And so this sort of makes sense. We're seeing, potentially we're seeing the influence of some sort of a marine particulate end member. Just both of those do that. What else do I have? Zirconium's hung out by itself. It tends to be somewhat controlled by, it's more susceptible to grain size, so physical size differences, but it seems to vary quite a bit. The other elements that we measured sort of hung out there by themselves. And then manganese was the only one that did this sort of middle, sort of mid-estuary. We see the max, and then it tends to decrease. And either it could be there's something that these, something's coming out of those tributaries that's probably carrying that signal. So we don't have tributary samples, but that would be a place that would be an example of where this would tell you to maybe start looking. So I think these plots are useful because they really are. We're looking at the data that we have, and we're looking at it sort of in a spatial sense, and so it helps. It's sort of the real data. We're going to sort of depart from that fairly soon. But I think they're useful because they do allow us to put it into a geographic context and identify areas that would be where you would look next to try and explain. So I would say from this part, I think what would be necessary would be, we certainly would want to try and better characterize the tributaries and complete the survey of them to try and get representative samples. I think we saw in many cases a lot of variability even within one tributary, and so you sort of have to, do we know the total range? We probably don't in this case because we don't. I would say that the tributaries at this point are undersampled, but so I think that would improve our ability to work through this. So now we're going to sort of work with the data and see what we can say about, can we explore different techniques that might allow us to trace some of these sediments by their unique signatures. And so I'm going to talk about the first two, linear discriminant analysis and optimal multi-parameter analysis. I'll use their abbreviations, LDA and OMPA. Let's see. So for these two, as I said, the composition in the tributaries vary quite a bit, but in this case, we're using the tributaries as end members. So we're assuming that what's in the main stem of the river is sort of going to be a mixture of what's coming out of the tributaries. I don't think that's a huge leap, but so because we did see differences not only so we took cores in the tributaries and we saw downcore differences as well as differences between locations. So what we did was we sectioned up, in some cases, different parts of the cores, and just to better express the variability. So even though we didn't sample 24 tributaries, we came up with 24 distinct end members. And so in some cases, for instance, I think it was in the upper Hudson, we broke that into 3 different end members, so that it would still find the right tributary, even though you might see some variability. So linear discriminant analysis, this was attractive because it's pretty much a mechanical separation of, it actually identifies things that belong in the same group. So the idea would be how similar is one sample to another. And that's how you would get groupings. Now, if we didn't constrain it, we basically would, if we analyze the tidal sediments, we would see which tidal sediments are similar to each other, which isn't what we wanted to do. So there's another thing you can do with this approach, and you can kind of constrain it with, by limiting, by basically you set it up in such a way that you constrain it to only use the tributary data. And so it'll basically, now what we'll get out of this is how similar are the estuary samples to a particular tributary, with the idea that the higher the probability, the closer it would be to that source. And so by constraining it in the beginning, we kind of are making it choose how similar it is to the tributaries and not to each other. The one thing that I did with this is what you get out of the outputs or probabilities, and basically the probability of it belonging to a particular group. And so you're going to get a lower probability for meaning that it wouldn't be similar to one particular sample, and if it's a higher probability, that would mean that it's closer to that tributary. However, because they all sum to 1, and we're looking at trying to basically reproduce the bulk chemistry of these, I decided to use those probabilities as fractions, just to see how well it worked. How well could we use those and reproduce the measured concentrations? So the numbers are there. Okay, so I'm going to show one of these. And this is what you get. You get sort of these probabilities. In this case, it was zone 36, which is the zone that's just south of the Catskill, which also includes the Catterskill. It all exits through the Catskill Creek. In this case, we were able to limit it not to 24 end members, but to 14. What you see is that for each, now these are samples on the bottom. So what this is telling me is that the bulk of this sample, say, is most similar to the upper Hudson, right? But you do see some variability. This might be Lohmann's kill. Interestingly, all the samples that are primarily yellow were ones that we collected in 2014, and those are also very similar to the Catskill and Catskill systems. So I think that's what this is telling us, is that we do see a shift, so I thought that was interesting. Let's see. So my attempt to reconstruct. So we have these probabilities which sum to 1. Let's use our n-member concentrations that we develop and reconstruct what we're supposed to get. And the 1-to-1 line in all these plots, again, this is going to be north of Poughkeepsie and south of Poughkeepsie. And in general, we see across these that the fits south of Poughkeepsie are not very good. And that certainly makes sense that we have inputs from other sources. And we see, in some cases, we see these linear, like either these limits or these linear features, which tells me that we, if none of our tributary samples have a high enough concentration that we measure in the estuary, we're not going to be able to reproduce it. And so you're going to see kind of a ceiling, and some of these plots had that. We also see areas that pretty much group off from an approximate linear relationship. I've highlighted these samples because they largely come from tributaries that were not sampled. And so it kind of tells me that, if we can go back and get some of these other ones, we may be able to improve this fit, for instance. But also, I think being able to get a handle on how variable are the concentrations that are leaving the tributaries is something that we also need to deal with. This is these flat lines that I was telling you about. So, clearly we see higher concentrations in titanium concentrations in the estuary that are not reflected in the tributary samples that we have. And so that kind of tells me that we're just not going to be able to go much higher than the mix. And it's and these are not just, for instance, we're not just using the titanium data. This is all the sources together. So it's not just the titanium concentration of the tributaries that would limit this. It's the fact that it needs other tributary sources to reproduce better, other elements. And so, but again, we see the impact here is that a lot of these samples are that fall far off the line are also from tributaries that have to be sampled. So lead and zinc, again, are not behaving very well at all. And I think, again, this is because we see an age effect. You're going to see samples, specifically with lead and zinc, that are going to be of different ages and have a much different loading of those contaminants. And in fact, the tributaries that we collect now may be much cleaner, and so the lead concentration might be much, much lower than what we see in the main stem of the river in certain areas. And so I would be very surprised if we could improve that, but it's just something to think about. So this will be interesting. So we had, in some cases, we had samples that were in the same location that were pre-storm, post-storm, and then I divided the post-storm samples into two different categories where it worked, where we had post-storm samples that we definitely thought were depositional. The idea would be if we said, well, this sample, is depositional, and it should have, what does that material look like compared to samples that were collected in the same place, but before the storms? Might that be a way to isolate material from a particular tributary, or at least see if it would emphasize it. So this is a little bit, again, so I had to read it a couple times myself to remember what I did, but so you get the probabilities within a tributary zone, and you sum all of the probabilities. So now we're sort of looking at a number for the whole zone. You sum all the probabilities from a particular source, and then you normalize those again. So let's see if this So in this case, this is just, we had pre-storm and post-storm. We couldn't identify necessarily any of these as depositional. And what you look for in these is a shift. So basically, do we see, you know, is there a pattern shift? And I think what we see in this case, so this would be for zone 36, you know, we see, so gray, you know, we see Bloemenkill, Catskill, and the upper Hudson, but we definitely see a shift in the post-storm samples towards the Catskill. So that's sort of this idea that we're, that we do see a shift in the similarity of samples. That, you know, after the storm, the samples where we had a pre and post comparison seem to be more similar to the Catskill than before. I will torch you as well. This was also, I think I picked this one because it's just south of the Catskill, or south of Sorekill, which is just below. And this really did show, we didn't have, you know, there's very, very little upper Hudson, and it seems like we do see sort of an emphasis on the input from the Catskill system. One more where we had a post, like a depositional category, and this seems to be a little bit more variable. This is south of the roundout, so this is now we're using all 24 of our end members, and so it's a little bit, you know, it gets unwieldy. And then I'm not going to show the plot that looks at basically everything else below that because we don't have tributaries to break it up, and the fits are not as good. And so I don't see too much here in the way of a really visible shift. We you know, we might see a little bit increase in the Catskill colors post-storm, but the depositional, not so much. But I would say for this, it was somewhat limited where we actually had samples that were, you know, in the same spot pre and post where we could do this comparison. But it's a way to use this data to maybe get it at that. So, you know, this idea of using predefined classes, so using the tributaries samples, that information, the end members, to kind of constrain this technique seems to be pretty useful. I guess I'll just shut that off. Sorry. Or better. So using the tributary information to sort of constrain this technique is useful, I think. It tends to fall apart the further you get away from what you're calling your end member. So it would be very interesting to try this with information from some of the lower tributaries where we see changes in the system. I think that would be useful. It also suffers a little bit in the reconstructions when you don't have, when your tributary samples, you know, they don't actually encompass the the estuary data. So if you have a mismatch in concentrations, it's very hard to reconstruct it. But that may be just a function of getting a handle on the variability. Other things that we might be able to pick up from this is like, for instance, lead. You know, it may be that we shouldn't use lead to try and trace source, and I kind of agree with that because it's got other things going on that we know cause problems. Unless there was a real, you know, maybe there was an isotopic signature or something that we could detect, but I think, so this helps you identify. So really bad fits, you might start to say that those are not suitable, something else is going on. And I think the pre-post comparison in this case did show some things closer to the Catskill system, but further afield, it didn't seem as obvious. I think I've probably said all this, and it's going to be kind of a, you know, so certainly better constraining the tributaries and also looking south of Poughkeepsie at some of those tributaries would be good. and I think we could design other tests that maybe focus on specific features where we see big changes. We also could, one thing that I think we could do more of is include other things besides chemical concentrations. There's physical parameters, grain size distribution, the matrix density, and maybe even additional elements that would enrich the data set to give us more ways to detect variability. But this seemed like it was a pretty useful technique. So now the OMPA. So this basically it's a least squares regression technique done we have non-negative constraints, so you can't have negative fractions. You can't have like a tributary taking material out. And the other thing is that we force the sum, so we can also impose a mass balance on our system, so that the fractions for any sample have to sum to 1. I got a picture. So this was modified from work that we were doing in oceanography. It worked very well for resolving water mass components, and I said, oh, this is actually quite similar to what we're doing. So I tried to work with it. Basically, the idea would be that for every bulk, so this would be say zirconium in this case. This would be the zirconium measured in a sample, right? So you construct a series of simultaneous equations, right? Where, well, so this is fraction 1. Now the fractions have to be the same for each source. So fraction 1 and the concentration from this n number 1 plus second fraction and the concentration there, and so on all the way through, so that all these fractions would have to sum to 1, and then the resulting concentration should be similar or not to your measured concentration. So that's sort of the idea but we're using all this data to simultaneously solve for the mass fraction. So this is how much material is coming. It would be attributed to a particular tributary. Yep. So I would say, by and large, the reconstructions are better for this technique. We see, certainly within, if you start thinking in modeling, the fact that we're getting most of the cloud of data is really more or less falling on a one-to-one line, which is nice. We do see some deviations downstream, but that's kind of to be expected. And also we may see these regions where we don't have probably as good a control on the tributary. So similar issues, although we don't see these sort of ceilings and floors that we see in the other data. So that was just an example of that, but this is in general, we see, I think this performs a little better, and it gives us a chance to say, well, so of the techniques that I worked with, I felt that this gave me the best estimates of the fractions. How much of one sediment sample could I attribute to a particular tributary? And so in general, we normalized everything. So those F's, they had to sum to 1. But one thing I did as I was examining this data, so this would be the mass balance. When you impose the fractions have to sum to 1, they're all gonna come on this line. But if you let that wander, what we see is kind of an interesting feature where we're under predicting the mass sort of upriver, and we're over 1 downriver. And this, what I think we're seeing here is probably the effect of grain size that I need to deal with. So you can add the same amount of stuff, but just finer and finer grains. So you'll get higher concentrations. But so these techniques really haven't addressed that, and that's why I think maybe if I could include them in the model, we would see we'd be able to sort of account for that more. But this kind of shows you that there's something else going on besides just the chemistry. Okay, let's see. So if we look at the fractions that are predicted, and again, these are just the mass fractions. So because we get that out of the discriminant analysis as well. If we look at the estimates of both of those techniques, it's interesting. Basically, I want to say, well, how much of the Catterskill skill, that fraction do each of the techniques predict, and where do they predict the high amounts of that? So this would be like downstream, how much Catskill sediment it makes up the total. And what we, in general, although there's a lot of scatter, we do see, both techniques showing increases, well, just below that system. But then we see these other areas that are clearly, both techniques are showing, increased amounts. And what I think this is clearly showing is these areas are the turbidity maximum. So we're seeing focused deposition probably is what's causing that. So you're just seeing more Catskill material deposited there because I think sediments are depositing there. But both techniques pick that up. I think that's it. So I'll skip the end member mixing analysis was interesting, but I think it's less concrete than these other techniques. But I won't talk about that today. It's in the report if you want to read. So the main conclusions from the study. So maybe Frank, you wrote this. So we were able to discern deposition and erosional layers using a variety of geophysical and geochemical techniques. We did identify areas of significant deposition and erosion. We see the distributions are not uniform, so there's a pattern. There's certainly a pattern of deposition, erosion, and that was the sand wave properties that Frank talked about. So I think that is it. You have anything to add, Frank?
We're running a little late. We have time for one or two questions.
Report times. What would you say to me if I was concerned about the environmental health of the Hudson River? Do these extreme events stir up enough sediment, bring different tributaries? Do I need to worry about stirring up PCBs in the Hudson River? Or is this just nature of work? The changes are so slow we don't need to worry?
Well, we've had several very low probability events happen pretty compressed in time, which is sort of goes with the predictions of some of the climate change. We're going to see, if those predictions are accurate, we're going to see increased number and severity. So maybe we can expect not these 500-year storms every 500 years. They're going to happen more frequently. I think. Well, what I think is that what we see day to day is the sort of the slow stuff, and it's these big events that deliver most of the material that really shift things around. And so I don't know if anyone has gone out and studied PCB distributions post-storm. I mean, so I would worry about if there are these large events that suspend a lot of material, especially since from Ralston's data, they have the ability to potentially focus on fairly small geographic areas. We saw a lot of material coming out of the Catskill. Should that happen in another area where there are contaminants, they're going to be released to the system. So I would be in favor of removing them so they can't get into the system like that. That would be the safe bet, or at least the worst the worst cases. But you can worry. I'm not sure what we can do about it, except maybe endorse, that the cleanups go ahead. I don't know if that's been finally decided, if they're doing more or not.
I mean, one thing that data shows, in these events, you don't just test deposition, so they're also eroding in some places. So you have to, and until we really can predict exactly where the erosion is.
Well, let me rephrase the question. Think about the ecological health of the Hudson River and trying to reestablish colonies of oysters. And do we need to worry about these extreme events?
I think so. I don't know. I guess to some extent, there might be impacted. You mean like oyster beds get buried by sediments coming up?
Some places.
Yeah. I mean, we didn't look. So the oysters are mostly like Tasselsy and Souse, and we know like in the Tasselsy there's exposed old oyster beds that have been buried by sediments over the last couple hundred years. So I think in the long term they're gonna be fine. I mean, and the question is like probably the nature of the event. Is this a dump a lot of sediment or say like swipe it off from the shallow areas where the oyster bed might be deposited? And you know, we see only the combinations that maybe like sediment coming from marine might bury them, but the big storm surge from sandy might remove all this fine sediment and leave them exposed. So it depends a little bit on the nature of the event. I think in the long term that might be fine, and maybe like warming up the waters would be a bigger problem than actually the sediments. And I'm not an oyster specialist, so they're like buried for a couple of months or maybe for a year. Would they survive then and come back? That's another question.
Yeah. All right, Nicole, go ahead.
Martin, go ahead.
I would, it seems like one of the big take-home messages to me was that the largest depositions were in the places where the channels were being dredged artificially. So aside from the river system just kind of coming back to some kind of more natural, authentic topography, in the areas that were outside of those channels, can you draw any conclusions about whether that sediment which was deposited is loose and easily resuspended, or you predict that it's going to kind of stay there, those places where they might be undisturbed by dredging? Do you expect that those sediments that's the new normal there, or that's just a temporary thing until they get swished around because they've just been deposited, so they're not very consolidated?
Yeah,
Can't tell you.
Well, we see some areas that, so one thing that we've done with a lot of the cores that we've collected up and down is lead. We can measure these lead profiles, and they tell us a lot about the age of the material, because lead in gasoline has a fairly identifiable pattern, and we see that reflected in many of the cores or parts of it, and so we can begin to sort of constrain the age of the sample. And we see many areas, I think the non-channelized of what you're describing, where deposition would be it would be fairly low deposition or very old, non-accumulating sediments, and their erodibility I think would be low. But and then you're going to go all the way to these unconsolidated fresh material. Now I think there was likely deposition, so there was likely deposition of a lot of that material in a lot of places that got moved around. Say from the storms here. So that would be unconsolidated material that might go in places that we don't typically see large scale accumulation. Like we skipped Newburgh because all the work we've done in Newburgh suggests that it's more like that we don't see very high accumulation there, except we had to sort of pare it down where we could study, and so we decided to go with areas that we knew to be depositional, thinking that those would be areas where sediment would be likely to go. Like we weren't surprised at all that we saw material in the Haverstraw channel, because it's a channel and it'll fill in quick or in first, basically.
And just to add on, so it's not only, it's like the highest amount of deposition is where it's being dredged, but it's also outside of the areas, in Haverstraw, outside of the dredge channel, there's deposition on the stretch between Kingston and Poughkeepsie where we see a lot, so that's not dredged at all. So there is definitely deposition also outside of the dredge areas happening, and
Yes, I'd like to know, was any studies made on the reservoirs, and do they collect enough rainwater? They have to increase their rainwater that they capture, and do they also release sediments to the estuary which is of significant value.
The reservoir, so like the Ashokan, and is that what you're talking about?
Yeah. Roundabout.
Yep. I don't know, we didn't study that, but, I know there is some tension over, and I don't know which of the, I think it might be the Ashokan, but there's very clear water and then very, sediment-laden water that mixes in. I think there's some, issue about how that's controlled in some cases, but typically they are not large, suppliers of sediment, I would say. That's, I mean, on some level, picking the reservoirs would be, we wouldn't want a real sediment-laden system, because it just makes a headache for people trying to keep the water clean.
You know, there's the opposite, so if you have a dam, it keeps sediment away from the system.
Terrific. All right, kept you here a long time. Thanks so much. Okay, we're in the process of getting some seminars together for winter and the spring. So pay attention to our website. We'll be announcing that shortly. And those of you that didn't have the opportunity to attend the Harbor and Estuary Program's wonderful conference 2 weeks ago, a week and a half ago, we have some materials that were handed out at that conference that are out on the tables. There's a State of the Estuary report, an action agenda, and some other goodies out there. So you might want to take a look at those. So have a happy holiday season, and we'll see you after the new year. Take care.